Welcome to Philosophy 2020 Basic Logic. This is the YouTube lecture series, and I'm your instructor, Nick McGinnis. Let's get started. Today we're going to be talking about the truth functional properties and how to define them in terms of one, truth functional consistency. Let's start with a brief recap of the truth functional properties. All individual sentences of SL must either be truth functionally true, truth functionally false, or truth functionally indeterminate. A truth functionally true sentence is always true. If you work out its truth table, the main logical operator will have a nice tidy column of T's underneath. A truth functionally false sentence is always false. The main logical operator is a column of F's underneath it. A truth functionally indeterminate sentence is neither of these. It has some T's and some F's. But these aren't the only properties we're interested in. We're also interested in truth functional entailment, truth functional equivalence, and truth functional consistency. A set of sentences A, B, C entails a further sentence D if it's not possible for A, B, C to be true and D false. If we imagine the first set as a group of premises and D the conclusion, we can say that A, B, C, therefore D is a valid argument when the former entails the latter. Two sentences are truth functionally equivalent when they have the same truth table. Finally, a set of sentences, including a set of one, is consistent if and only if it's possible for all members of the set to be simultaneously true, and the set is going to be inconsistent otherwise. So what we're going to do today is define all these properties in terms of one of them, consistency. Why is this important? Well, in our next lecture, we're going to introduce a method called truth trees for determining truth functional properties of sentences and sets of sentences. And defining all the truth functional properties in terms of one of them allows us to run the same procedure, a consistency check, to answer questions about truth functional properties. For now, let's look at how to use consistency to define the other properties. Consistency is a very weak property. It's easy for sentences to be consistent. It merely has to be possible for them to be all true at the same time, under some truth value assignment. Consider the set if P then Q, Q not P. Is this set consistent? Can all these sentences be true at the same time? Sure. When Q is true and P is false, then each sentence is true. What about either P or Q? If not P, then not Q, not P. Can all these sentences be true at the same time? No. This set is not consistent. If not P is true, then the conditional if not P, then not Q means that not Q is going to have to be true as well. But if not P is the case and not Q is the case, either P or Q can't be true. So not all the sentences can be true at the same time. If some of them are true, some of the other ones are going to have to be false. The set is inconsistent. Consistency and inconsistency apply to sets of one sentence as well. A sentence can be consistent or inconsistent with itself. If a sentence X is inconsistent with itself, then there's no case where the set of sentences whose sole member is X are all true. Consider the sentence P and not P. It's clearly truth functionally false, but it's also truth functionally inconsistent with itself, i.e., if I make a set of sentences with this sentence P and not P as its only member, then there's no way for all the members of that set to be true, even though it's only a set of one. So here we have our simplest case. A sentence X is truth functionally false if and only if the set comprised of X is truth functionally inconsistent. What about truth functional truth? Well, here we do something a little clever. The negation of a truth functional truth is, by necessity, truth functional falsehood. This is because the negation operator reverses the truth values it acts upon. So if it operates on only T's, it's going to output only F's. But we already know how to use consistency to check for truth functional falsity. So if negating a truth functional truth produces a truth functional falsehood, and we know how to check for that, then we have a definition for truth functional truth. We negate the sentence and check to see if that negation is inconsistent. So consider the sentences either P or not P, and not the case that either P or not P. So the first one is an unnegated truth functional truth. Now the second one is the same sentence but negated. And we see that it's truth functionally false and inconsistent with itself. And this gives us our method. A sentence X is truth functionally true if and only if the set comprised of not X is truth functionally inconsistent. What about the indeterminacy? Well, we have checks for truth functional truth and truth functional falsity. But if saying X is consistent and saying not X is consistent, then it's neither truth functionally true nor truth functionally false, leaving only indeterminacy. So there's no check for indeterminacy, rather we check for truth functional truth, truth functional falsehood. And a sentence is truth functionally determinate if it turns out that it's neither truth functionally true nor truth functionally false. Okay, what about equivalence? Truth functional equivalence can be defined in terms of inconsistency as well. So I'll give you the definition, then I'll give you the rationale. Two sentences x and y are truth functionally equivalent if and only if the set not x if and only if y is inconsistent. So this works because the biconditional, if and only if, and I'm using the equal sign because of character limitations, but I mean the biconditional. The biconditional outputs true whenever the truth values of its inputs is the same. So any two equivalent sentences with the same truth table, if they're joined by a biconditional, that biconditional is going to always output true. So two equivalent sentences joined by a biconditional creates a truth functional truth. And we know how to check for truth functional truths. We check for the consistency or lack thereof of the negation. Maybe an example would help. So here we have two truth functionally equivalent sentences, if p then q and either not p or q. And they have the same truth table, true, false, true, 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 false, true, true. Here, if we join them by the biconditional does its job, and we get a truth functional truth. Then we negate this biconditional, which flips the trues to falses. So we have a truth functional falsehood. So it's inconsistent to affirm that the biconditional is false. So the biconditional must always be true. So it's a truth functional truth to put together two equivalent sentences with a biconditional. That's exactly what we were verifying. So that's how we check for equivalence using consistency. Now you might be wondering why the emphasis on inconsistency as opposed to consistency. Well, as I said earlier, consistency is a very weak property. Sentences being consistent doesn't tell us much. It can't differentiate between being truth functionally true and being merely truth functionally indeterminate. If a sentence is consistent, that means it could be true at least on some one truth value assignment. Truth functional truth means it has to be true on all truth value assignments, which is different. So at the level of a single sentence, inconsistency and truth functional falsehood line up. They become essentially the same thing, because an inconsistent sentence can't be true. It's always false. So inconsistency pinpoints a specific property. So we can use inconsistency to determine the other properties with some clever use of negations. That's why inconsistency seems to be the thing we're focusing on. So this leaves us with entailment/validity. Here we proceed very slightly differently. An argument is valid if and only if the set consisting of the premises and the negation of the conclusion is inconsistent. So we keep the premises as is, but we negate the conclusion. If this is inconsistent, we have a valid argument. Right? If this is inconsistent, we have a valid argument. Why? Well, the definition of validity is that it should be impossible to have true premises and a false conclusion. And this is exactly what we're checking by negating only the conclusion. We are verifying the consistency of true premises, false conclusion. If it's consistent, if it's possible to have true premises and a false conclusion, the argument is invalid. Because it's possible to have true premises and a false conclusion. If it's inconsistent to have true premises and a false conclusion, the argument is valid. Because it's not possible to have true premises and a false conclusion. So let's look at a couple of examples. This is a valid argument. A very simple one. If P then Q, P therefore Q. So what do? We check the consistency of the set of the premises and the negation of the conclusion. In this case, the consistency of if P then Q, P not Q. We can do this really quickly. Just think, you don't have to do the full truth table, just think about it. If P and not Q is the case, then P is equal to true and Q is equal to false. But if so, the truth table of if P then Q specifies that if P then Q must be false, because if P is true, Q is false. So not all sentences can be true at the same time. The set is inconsistent. That means that the argument is valid, because it's not possible to have true premises and a false conclusion. If we look at the set comprised of the premises and the negation of the conclusion, we see it's inconsistent to affirm it. It's inconsistent to affirm that the premises are true and the conclusion is false. If it's inconsistent to say that the premises are true and the conclusion is false, we have a good argument, we have a valid argument. Let's look at an invalid argument then. This is a fallacy of a very famous fallacy. So it's affirming the consequent. You can look it up on Wikipedia. It goes, if P then Q, Q therefore P. So we check the consistency of if P then Q, Q not P, right? Premises, negated conclusion. So if Q and not P is the case, if it's true, then P is equal to false and Q is equal to true. But then, if P, then Q is true, because P is false and conditionals with true antecedents are always true. So the set is consistent, and the argument is invalid. It is possible to have true premises and a false conclusion, specifically on the truth value assignment P equal F and Q equal T. That's all I have for today. We defined truth functional properties in terms of consistency. Next time we're going to use these in the method called truth trees.